will be presenting on linkages between NREL's Dgen, Reopt, and Sam models, along with my co-authors, Michaela Sizemore, Paritosh Das, and Jane Lakshan. Today is the first in our summer series of SAM webinars this year. So today we're talking about these three different models. Next week, we'll be talking about financial models for utility scale projects in SAM. In August, we'll have a session on modeling utility scale photovoltaic projects in SAM. And then in September, we'll have a session on modeling behind the meter batteries in SAM. So the dates are on the right side of the slide. You can register for free on the SAM website. And then after each session, we'll record, we are recording these sessions, and we will post the recordings to the SAM YouTube channel, which is also accessible through the SAM website. Our agenda for today will introduce all three of these models, and then talk about the existing Dgen and Pi Sam interface, and then talk about our two new implementations for this work, a interface that links the SAM GUI with Dgen, and an interface that links Dgen and Reopt, and then we'll have time for questions at the end. So feel free to type your questions in the chat whenever you have them, but we will wait until the end to answer them. As far as Q&A options, this slide demonstrates how to enter questions depending on which interface you're using, the desktop application or the web instant join viewer. And with that, I'll hand things off to Paritosh to introduce Dgen.
Thanks, Brian. My name is Paritosh Das, and I'm a research engineer at the National Renewable Energy Laboratory. Thanks, everyone, for taking the time for going through the key updates through the linkages about the different models that we will be talking about today. I think it would be really helpful for us to gather your feedback or comments or anything that you feel we can add or change through our modeling to help the user community to make it much more user-friendly, but also add functionality that you guys think would be much more helpful for your analysis or for specific data sets that you think would be helpful in the analysis as overall. I'll talk through a specific project through which a lot of this has been possible. A lot of these developments that we would go through in this particular session would be possible. And maybe looking forward to your questions and comments as we move along, not only today, but all around this year and next year to the timeline of this particular project. So the model that I would be talking about right now is NREL's distributed generation market demand model, or in short called the Dgen model. This is an agent-based forecasting model which forecasts the adoption of rooftop solar, behind-the-meter storage, small-scale wind, and geothermal technologies by different geographical regions and different sector classes from 2022 till 2050. So we do have a 2-year time modeling time frame that we move along with. So from 2022 till 2050 by a 2-year modeling time zone. This modeling framework basically looks at the consumer's perspective rather than the utility's perspective to see what are the drivers of adoption, primarily looking through the lens of rooftop solar and storage, and what policies and how incentives and how different combinations of sectors and where we are located play a major role in convincing or making a decision for a consumer to adopt a particular technology or a combination of technology altogether. We have used this model very predominantly in a lot of our NREL's analysis, starting from the solar future study, storage future study. You get a feel of all the future study who are coming out with solar, storage, and distributed wind. But we have also been used this model in analysis for the Los Angeles 100 study and the currently going on the Puerto Rico 100 study as well. Some current work is also underway as a second part of the Los Angeles 100 study with respect to specifically looking into equity strategies and how equity plays a role in adoption of newer technologies and where they are located. and what incentives do make sense to make those adoption much more equitable overall. Next slide, please. As I was mentioning, this is a very bottoms-up, granular agent-based model, which looks at, from the consumer's perspective, right from the most granular that we have right now is on the county level. So we develop a lot of our data sets on a county level, adding where we are located, solar resource zoning, population load, what utility those consumers they are in, what building types they are in, going into much more deeper aspects of buildings as well. Have used LiDAR scans of buildings, looking into the tilt and azimuth shading, how much would be technically possible on a particular building type, and then moving from there into a lot of the financial aspects of things. What is the NPV? What is the cash flow? And then thinking about, even if it's economically feasible for a particular consumer or consumer classes, how does that play a role in finally getting adopted in the market? So the point being that the aim is to develop a lot of these basic granular data sets and then overlap them on top of each other to derive these statistical agents that help forecast these adoption decisions that these consumers or statistical agents make as throughout the modeling framework. So thinking from outputs perspective, so what you would see is looking at, maybe take an example for Colorado, say Excel's territory or Colorado's overall as a state, where we are expecting more distributed PV and storage to come in. Why, and are there particular incentives that are playing a role? Is there a particular, are the cost being the major factor, or the lowering of the installed cost being one major factor? How storage is playing a role as well, both on the charging side and the discharging side. Thinking from all those perspectives, how does it eventually end up as an adoption decision for these agents, and finally ends up being as forecasted capacity and generation of rooftop PV coming up in the next 10, 20, 30 years down the lane. And the agent-based modeling helps us give that granularity that we can shift along from that county level aspects much more easily with, we can aggregate them up and get more perspectives if you're looking at a particular utility or as a state as a whole. Next slide, please. So this is the project that I talked about in the beginning. It's called RIDER, short form for Resilient Planning for DERs, primarily looking in specifically for data standards and multi-DR evaluation. So this is CETO, the Solar Office funded, DOE funded 3-year project. We are in year 2 right now, and a lot of the developments that you would see is part of this particular project that has happened through different modeling capabilities and how we are integrating not on the data side, but also on the modeling capability side. So this project is basically looking into how consumers have been making decisions as standalone. So as standalone, I mean, like, people have been thinking through people adopting rooftop solar, but increasingly we have seen people making decisions of adopting these different groups of technologies as a package. So rooftop solar with storage has become a major trend right now in the Northeast, in California as well, where the attachment rates for rooftop solar has been with a storage system as well. How does that play a role when we combine these technologies together from a consumer's perspective, from all the calculations, economic calculations, and the technical feasibilities, and how does that eventually end up in forecasting? But what we have taken a step further is added energy efficiency, appliances uptake, and electric vehicles uptake as well. How combination of rooftop solar, storage, energy efficiency, and vehicles play a major role in consumers' mind in terms of what do they think, one is better or the other is better or the combination is better, looking from the financial aspect as well and the market adoption perspective. So it gives a holistic picture of standalone, but a combination as well. That's the broader theme of the Rider project. But within this project, there are basic three aims that we want to achieve as well: is improved data standardization and access, much more granular data sets for the user community that are publicly available. So we'd be publicly posting a lot of our data sets that we develop on our agents on much more granular than the county level as well. Develop new standardized data sets, agents, and new modules for incorporating these new technologies as well. And our model is open source right now, so we have a link that I think Brian would present right at the end, and people can go and check out the open source version. We would be pushing more and more updates from this particular project to the open source code branch that people can try out, and the newer data sets, updated data sets as well. The third major piece is dissemination and outreach, where the major aim is to provide technical assistance, technical guidance with respect to data, with respect to analysis and code to ISOs, RTOs, utilities, state and local energy planners, basically people who think the analysis would be helpful for them or their stakeholders to come up with a decision or see how much forecasted rooftop PV storage, energy, EVs, they're expecting in their territory, in their state, in their city to come up in the next 20, 30 years. And is a particular policy that's helping guide that out, or they can even try out newer policies, evaluate newer policies, newer tariffs, electricity rates that might play a role in incentivizing these technology adoptions in the near future. So I would end this, at least in this particular section, about any guidance, any help. And if you would like to be part of this particular project to be much more in line, in sync with what's happening as we move around from one quarter to the next quarter, on the next 2 or 3 quarters, please do send me an email or send me an email on the Dgen website as well. Register there for to getting regular updates for any updates that we have through this particular project. We would very gladly would like to have your feedback, your suggestion incorporated as we move along from year 2, within year 2 as well, and also in year 3, both on the development side, on the model development, data development, but also primarily on the data dissemination and the outreach pieces, where any technical assistance that we can provide to your companies, your utilities, or the city and state planners, that would be of great help to us as well. With that, I'll send it over to Brian.
Thank you. So to introduce System Advisor Model and PV Watts, these are free software that enable detailed performance and financial analysis for renewable energy systems. SAM is available as a desktop application. PV Watts is a web tool and an API. We provide access to a software development kit, including the Pi Sam Python package, which will be featured prominently on subsequent slides. All of the package is open source with extensive documentation and user support. Overall, the models in SAM tend to take this structure. We pair a performance model, which takes in things like weather data, system specifications, and losses, and calculates things like monthly and annual production of renewable energy, capacity factor, and other operating parameters. And then we provide that production data to a financial model, which combines that with things like costs, incentives, financing, and compensation, and calculates metrics such as net present value, or NPV, LCOE, or the levelized cost of energy, payback period, operating costs, revenue, and taxes, and thus allows for predictions of the value of a project. These are the technologies that are currently, technologies and financials that are currently modeled in SAM. Today we'll be focusing on the energy storage technology and the residential and commercial financial models, but all of these are available in both the desktop software and the software development kits. So to get into a little bit more depth on Pi Sam is a Python package that enables users to run the underlying modules that make up the simulation in SAM. If you're going to download this into your Python environment via pip or conda, the package name is NREL-Pi Sam. If you just download Pi Sam, you will get something else. But instructions for that are on the Pi Sam repository, which we'll have a link to at the end of the slides. And within Pi Sam, we're calling unit compute modules of the SAM simulation core code. So that's just like one of the technology or financial models that we were discussing on the previous slide. For example, the PV model or the battery model or the utility rate code. So a single simulation then to match what the SAM GUI does when you hit the simulate button is a process chaining together multiple unit modules. So here you have to worry about the order and sometimes what information needs to be passed from one module to the next. There are helper functions that make that information passing relatively easy, but depending on exactly what you're doing, you may have to do that with individual lines of Python code. And then the graphic at the bottom there is the generic system battery commercial owner documentation, which represents one of the sequences of compute modules that pretty closely matches what's being run in the Dgen software. So PySam, SAM, and other software development kits expose these unit modules within the SAM simulation core so they can be customized and embedded in software applications like Dgen. However, PySam does not contain all of the features of the SAM GUI. There's a number of calculations that are embedded within the SAM GUI that we have not yet finished translating over into PySam. That's a bit of a work in progress. So for example, things like construction financing costs are an input that goes into PySam. The SAM GUI would help you calculate that given a project's installed costs, but that's something that you may have to re-implement in Python at the moment, depending on your use case. And there are warnings for variables that require that, or variables that have dependencies and might need to be changed together throughout the documentation. The third tool we'll be discussing today is Reopt, which is a platform from NREL that optimizes the planning of generation, storage, and controllable loads to maximize the value of integrated systems. Reopt considers the electrical, heating, and cooling loads for a building or campus, and technologies, considers those loads and technologies simultaneously to identify the optimal technology or mix of technologies. And so this transforms potentially complex decisions into actionable results for building owners, utilities, developers, and industry, and can be used to guide analysis decisions for investments in economic, resilient, and sustainable energy technologies. This graphic shows some of the inputs and outputs of the Reopt platform. So resources and technologies options are listed on the left, which includes PV, wind, different types of storage, and different types of flexible loads. Cost drivers are listed at the top, including incentives and financial parameters. And then the outputs for the cost-optimized minimum cost solution are listed on the right, including battery dispatch and net present value. So this slide shows a range of possible users for Reopt, including researchers, developers, building owners, utilities, and industries, with possible questions that Reopt can answer on the bottom, including what is the optimal size of DERs to minimize the cost of technology, which is the question that we're focused on today. So this slide shows the types of trade-offs that Reopt is making as it sizes and dispatches systems. So the black line shows the original electric load of a hypothetical building. Blue shows when the optimal PV system is serving the load. The battery charges in dark gray and discharges in orange, and then grid serving the load under the optimal solution is in light gray. So you can see in the horizontal set of lines a case where the PV and battery systems combine in order to reduce the peak demand and reduce peak demand charges in the utility bill. And then the orange and gray demonstrates load shifting, or buying energy when it is cheap, and then discharging the battery when it is expensive. And just as a note, Reopt and SAM in this case are solving similar problems. Reopt is doing this via an optimization, which constrains the equations that they're able to use a little bit into non-convex equations, but then it does spit out that optimal size. Whereas SAM, we have greater flexibility in the equations that we're able to model. So for example, we can use a detailed voltage model in the battery as opposed to a flat efficiency, but then you have to rely on tools like Reopt or parametrics in order to size systems. So moving on to the existing Dgen and Pi Sam interface, this is something that you could see if you look at the current open source code. So part of this interface is translating the Dgen agent data that Paratosh was talking about into the Pi Sam format. There's little bits of different naming that the Python code has to handle in order to set up a Pi Sam run from the Dgen data. The Dgen data does include PV generation profiles already, so it has hourly kilowatt hours per kilowatt that then can be multiplied by system size during sizing, which leaves the remaining model chain that Pi Sam needs to run as the battery compute module, the utility rate 5 compute module, and the cash loan compute module. So this determines whether a battery should be deployed with PV for any given agent, and then what the expected net present value and payback period is for that agent based on the utility rate savings. In some cases, for both of these, we are using SAM's defaults that come as a part of Pi Sam. And so whether we're using both the residential and commercial models in SAM, use the cash loan compute module with different defaults, but the defaults in this case vary based on whether the agent is representing a residential agent or a commercial agent. So outputs after Pi Sam runs, after we execute those 3 compute modules, the outputs include the system size, the net present value, the agent's bill saving, and the payback period. So in the existing code, Dgen is iterating through multiple sizes and picking the best net present value. And then once the best net present value available to an agent in a given year is determined, that's fed into some of the adoption curves. So agents with shorter payback periods and higher net present values are more likely to adopt, and agents with longer payback periods and lower net present values or negative net present values are less likely to adopt or won't adopt. And with that, I'll turn it over to Michaela to talk about how we are expanding that interface.
Yeah, thank you, Brian. So over in the Dgen model, we are now going to be leveraging the SAM output JSON files in order to update kind of what we're already using with that Pi Sam integration, and then to expand on it by using the JSON files. So right now, the SAM model allows users to export their system input parameters into a JSON file format. From there, we are leveraging the built-in Python functionality for reading the JSON files, and then utilizing those parameters and putting them into our Pi Sam functionality that we already use. The overall benefit of this is that it will reduce our hard-coded values while also increasing the model accuracy when we are running these scenarios. The next slide. So just as a quick start for how a user can export their JSON file from their SAM model. So the first thing you're going to do is just create a new SAM project. Next step from there is to go over to the drop-down, there's a drop-down box next to the project name, and you'll select Generate Code at the bottom. From there, you will select JSON for inputs from that little code language box that pops up. And then finally, you'll select a save location and click Open, and the JSON file will be placed in wherever you chose as your location, and will be saved with the format of the project name .json. Next. So just as a proof of concept of just the current impact that we've seen from integrating the JSON file with our Dgen model, on the left side, you will see just an example of some outputs from the Dgen model. We have just some bill savings accounts or amounts. So on the left is without the JSON input. So this is just our standard Dgen model, how it runs, and then kind of those values when they came out. And then over on the right-hand side, you'll see that the output from when we added in the JSON file inputs. And as you can see, there are differences between kind of those values that we are getting. And this is only just changing the utility rate 5 function to pull instead from hard-coded values, and then instead using the JSON input files from the SAM model. Next one. So currently, the way that we've been able to implement this is just making a couple of little updates. So to the actual dgen model.py file, this is the file that our users are really interacting with the most. It's really just a simple switch of just having the model look for a JSON file input, and if it's not there, it'll default back to just the hard-coded values. And then underneath that, you'll see a little snippet of how we've updated to pull from the JSON file. And so instead of it being, again, a hard-coded value like you'll see, or well, I guess you won't see, so instead of it being a hard-coded value, we have the model go through to our JSON file that was inputted, finding a specific key, and then it'll extract the value from there and feed it into Pi Sam with the utility rate function. Then we can go to the next slide. I guess I'll talk about it there. So the next steps that we are anticipating for this integration is to actually reconfigure the original Dgen financial functions Python file, instead to now accept a JSON input or to default back to what it was doing before if the user does not give us a JSON input. So this way, we just want to make sure that we're reducing the overall addition of code to our software, and then also kind of keep the user accessibility kind of at the front of our integration here. We also will be going through and testing edge cases for the SAM options. For example, if a user does a scenario without a battery and our Dgen model is looking for a battery input, we don't want it to fail just because of something like that. And then, of course, we also want to make sure that a user does not have to give an input JSON file and they can still get a model output. And then we will also be putting in 2 more Pi Sam scenarios, which will be for the battery and cash loan options from Pi Sam. And then I will be passing back over to Paratosh.
It's to me.
Or to you? Okay.
Yeah. Thanks. Yeah, so the last piece to cover here is the Dgen Reopt interface. So there's a couple of different ways that you can access Reopt. There's a website, web application, where you can input data via a web page. There's an API where you can access the web backend programmatically. And then there's also a Julia repository where you can download the code and run it locally and do the optimization locally. For this integration, we chose the Julia repository because we needed to be able to do things programmatically, but we're concerned that Dgen runs would potentially exceed the rate limits of the API. So in order to do this, what we needed to do, we actually put this in between 2 different of the Pi Sam steps. If you've used SAM extensively, you may have noticed the size and dispatch option on the battery page, where SAM will call out to Reopt and get back an optimal size and dispatch profile for the battery. So we've expanded on that for the Dgen interface. So we used the existing Dgen translation functions that I was talking about a few slides ago to get things into the Pi Sam data format. There's a new function within Pi Sam that we released with version 4.2 that allows users to get back a JSON object that works for the PV plus battery optimization that we're trying to do here. The previous one, you would assign just the battery. This one configures the Reopt call correctly to do both. And then we pass that off in the Reopt JSON format to Reopt via PyJulia. So then Reopt runs, so PyJulia is just a Python Julia interface, since Dgen is written in Python and Reopt is written in Julia. And then we're able to run Reopt via that method and get the system size back. So then we pass that system size back to Pi Sam and use Sam's heuristic battery dispatch in order to get an estimate of value for the battery. And then everything's formatted in the existing financial metrics that Dgen expects for adoption decisions. And when we open source this version of the code, it will just be a simple true-false in the config file. A lot of these details might be buried below the level that a lot of users will see them. So for preliminary results with running this, we just looked at one county in Delaware that we've been using for tests in the Rider project and tried to estimate the adoption between 2020 and 2022. And what we saw was with Reopt, 8.7 megawatts of distributed PV were adopted in 2022 versus the previous method with SAM, 12.6 megawatts of distributed PV were adopted. Generally, when we dug into that, we found that the system sizes for individual agents were a bit smaller, and that's because Reopt was finding shorter payback periods than what SAM calculated for most agents. As I said, we haven't released this yet. There's still some QC to do around utility rate and financial representation, making sure that all of these interfaces are passing back and forth apples to apples values. And then we are planning to, as a part of the release process, do some validation with historical data. On this last slide, I've included links to the SAM website and all of the different software repositories that we used and linked between. And with that, I think we're ready to take questions.
Yes, hello everyone. If you have a question, please feel free to type it in the chat box or the questions box, or you can also raise your hand. And if you raise your hand, we can unmute you if you want to ask a question by voice.
Brian, as the questions come in, I had maybe a clarification for, it might be confusing for a couple of our users, like why we selected JSON format to be the link between both on the SAM outputs and on the Dgen outputs as well, and why is there's a couple of exports of a particular scenario that you can do from SAM, but why JSON is at least the preferred version that we have used right now. And I think one of the reasons why we selected that was primarily looking into a lot of our rate calculations, at least within Dgen, has been using a JSON format. And what we found is, I think SAM has a very advanced capability of designing a rate or updating a rate or electricity tariff for a residential customer or a utility customer, change their different tiers, change their fixed costs. So if we want to test a new rate, and it's much more complicated to do that programmatically within Dgen, it becomes far much easier to design that particular rate as a case within SAM, and it's much easier to export that back into Dgen. And it might be a newer rate that somebody is evaluating, or just trying to see what a particular change in a particular rate might be, just increasing the tiers or just increasing the fixed cost as well, or maybe a time of use rates and how changing different versions of the time of use timings or rates would affect synchronizing better with the storage and the PV pieces. So that was a bigger push for us internally as a team to see how we can do that better and a much easier way than to go into code and change everything to design a simple rate. Hopefully that was helpful on the overall context for some of the JSON linkages. Brian, did you have a comment on some of the Reopt interactions that you saw come in and some of the challenges, other than the API limit calls that we have been seeing on our end?
Yeah, so I think I just want to give a shout out to the Reopt team for helping us work through some of the data interface challenges. There were cases where, just as a geeky programming note, some of the data structures were getting flipped around a little bit between Python and Julia. So thanks to Bill especially for helping us work through that. I think the two other comments about the state of the code. We're still gearing up to get this a little bit multi-platform and multi-process. things. The run that I showed here was done on a Windows machine, single-threaded. And I think the surprising part about that to me was that it took about the same amount of time as the iterative PySam run took with 6 cores. So I think one of the advantages that we're looking for from this Reopt integration is that the Reopt equations are able to get that optimal size in one run of the equations, whereas with SAM, we have to run, particularly in the residential case, some potentially slow battery dispatch code several times in order to narrow down the system size. So fingers crossed that those results will hold up as we scale this up, but it might be a good speed up for Dgen if it works out.
Absolutely. I think it'll be super helpful in terms of the users as well. I think just looking at like what maybe a county or a city or a state that may be running. So having a multi-process work to shorten the time frame of the run, I think would be super helpful both as internally as a team, but as for our user base as well. I think one question for Michaela. Michaela, do you have maybe a rolling timeline through the Rider project when people should expect a lot of these code updates to finally flow through our open source code branch?
Good question. So I think it really will be coming down. So the actual implementation, because we've already laid the groundwork, should be pretty quick. I think that what will be kind of a challenge from there is just testing and making sure that, we kind of encompass all of the edge cases there. I would love to say that we could hope to see this in the public-facing Dgen model, hopefully by the end of the year. I know that that's kind of far out, but it would be good if we could, bring it back even, I'll say 2 to 3 months would probably be the most realistic there. So we'll see somewhere within the next couple months. We will more than likely see some sort of implementation of this for the public Dgen model.
Gotcha. Thanks, Michaela. Yeah, I think that would be awesome if people can try it out and see some of those variances, flavors come through. But most importantly, also keep an eye out for more updates regarding the other pieces that I was talking about. So we talked about Reopt, SAM, Reopt, Dgen, but there's the bigger push as well that the team is making on the energy efficiency and the EV aspects of things as well as a technology piece. So those are in the process of being integrated on the data wise and also on the code wise. On the development pieces, new modules are being developed as we speak, and data sets as well on a much granular level, even much more granular than county data sets. So those are also expected to roll through slowly, integrated within the model and tested to see some of those actually make sense and remove some of the bugs that might have come up because it's a complex one with aspects of newer data, newer code, and also a combination of complex models such as SAM, Dgen, and Reopt coming through. So a lot of quality control and testing goes into some of these model development and data development as well. So keep an eye out for as they roll into our open source branch, but also into our publicly available data sets as well. With that, Paul, do we have any other questions come up?
I'm not seeing any questions or raised hands.
Gotcha. If we can end a little early as well if people can get back some time as well. But I'll just reiterate at the end that if people have more questions or people want to part of the project and or want to be kept up to speed with the model developments or the data developments that are planning to come roll out in this year and next year, or with technical assistance as well, please reach out to me, Brian, or Michaela. or Jane, and we'll be happy to connect you to the right folks.
And there is a question that just came through asking whether this integrated tool set would be valid for other countries, specifically for Brazil or South American countries.
Good question. I think the code should be still valid. The major development would be on the data sets. I think we have the data framework standardized for the US, at least on the states and the county framework, but I don't see a problem adapting the core data sets to a newer country, and we have done that for other countries as well, such as for Canada, Mexico, Colombia, and in India. So I think the major update would be on the core data sets, at least on the agent data sets, and if we can get them into a particular granularity about maybe it's districts rather than counties over here, or a specific granularity that works well within Brazil, and all the other data formats are aligned, such as load, location, tariffs, and everything else are aligned to the framework that we have standardized right now. I don't see a problem making that work for other international countries as well. Anything else, Paul?
Nothing that I'm seeing.
Awesome. If there's nothing else, I would thank everyone for their time, and the team as well, Brian, Michaela, and Jane for the valuable feedback in covering the different sections in this particular presentation. And hopefully people get to connect with the project and the developments with as they come along in this year and next year. Any closing thoughts, Brian, Michaela?
No, thanks everyone for coming.
Yeah, thank you.
Thanks, everyone.
Okay, goodbye. And with that, we'll close out the session.